Section 11.2, Techniques for Evaluating Limits. So students will be able to evaluate one-sided limits of functions and use different techniques to find limits of functions algebraically. So the first thing is the limit of f of x as x approaches c from the left side. So the other day we talked about being able to find a limit, how it had to approach the same value from the left and the right side. Well, we can also look at one-sided limits where you only have to look at one side. So on this one you'll see the limit as x approaches c. But look right there, that kind of negative value right there. That means from the left side. So if you have as x approaches 2, and then that negative up there in the right-hand corner of that number, then that means as it approaches it from the left side, that's a one-sided limit. So the limit of f of x as x approaches c from the right side, or the positive side, you will now see the number and then a plus sign. So you can find one-sided limits, but you have to use the correct notation to be able to do that. So to find the limit left and right of 0, I have a graph here of the function f of x equals the absolute value of 2x divided by x. Now in the graphing calculator, it's not going to put those open circles for you. You have to understand that x equals 0. It is undefined, so those values you will not have. And also you'll notice them in the table when you go to do it anyways. But we're going to look at the left and right side of 0. So find the limit left and right of x equals 0. So the limit as x approaches 0, and then once again you're going to see that negative to the right of 0 in the upper corner there. That means from the left side. So as x approaches 0, alright, we're getting closer and closer and closer to 0. As you get closer and closer to 0, what is the y getting closer and closer to? Well, it's actually staying at that value of negative 2. So the limit as x approaches 0 from the left side would be negative 2. The limit as x approaches 0 from the right side, so now the positive side, so from the positive side as you get closer and closer to x equals 0, the y value is getting closer and closer and actually stays at y equals 2. So both sides of those limits exist, but on C it says the limit as x approaches 0. So from what we talked about the other day, the limit as x approaches 0 of this function has to approach the same value from both sides. And you can see from the left side it approaches negative 2, and from the right side it approaches 2. So does this limit exist? And the answer to that would be no, the limit doesn't exist because it is approaching two different values. And so we have the existence of a limit if f is a function and c and l are real numbers, so as long as x approaches this real number c and the limit is also a real number, then the limit as x approaches c of f of x equals l, if and only if both the left and the right limits exist and are equal to that same value of that limit l. So once again, we kind of talked about that before, but just to kind of reiterate the existence of a limit, it will exist if and only if both the left and the right limits exist and they are equivalent or equal to the same y value there. So I have a graph. I want you to use the graph of the function f of x to find each limit. So I want you to pause the video and I want you to go through this and see if you can answer all 5 of these, and then we'll kind of, we'll talk about them as we go through. So pause the video and see if you can answer all 5. Okay, so let's see how you did. The limit as x approaches pi of the function f of x. So where is pi? Pi is located right here on the x-axis. So as it approaches pi, so as it approaches it from the left and as it approaches it from the right, what is the y value getting closer and closer to? And that would be 0. So right there, the limit as x approaches pi, pi is part of the graph, and that would be at y equals 0. On B, we're looking at a right-handed limit. You have as x approaches negative pi over 2 from the right side. So negative pi over 2 is right here. And so from the right side, as x gets closer and closer to negative pi over 2, what is that y value getting closer and closer to? It's getting closer and closer to the y value of 2. Okay, so the limit as x approaches negative pi over 2 from the right side is B. C is as x approaches pi over 2. So pi over 2 is right there on the x-axis there. And this is not a left or a right-handed limit, so it is just the limit as x approaches pi from the left. So as it gets closer and closer and closer from the left, and as it gets closer and closer and closer from the right, you can see there's an open circle at pi over 2, but it doesn't matter. It's as it approaches. So what is it getting closer and closer to from the left and the right side as x approaches pi over 2? And that would be -2. Now there is this point up here that kind of fills in that circle, but it's not. That's not your answer. That's not what those values are approaching. The values are approaching and getting closer and closer to -2, not getting closer and closer to 1. So be careful. Just because there's that point there doesn't mean that's what it's approaching. It's definitely not approaching that value. D, the limit as x approaches 5 pi over 2. So 5 pi over 2 is all the way over here. The graph has an arrow, so it does continue on, so you just have to think in terms of that trig function, what's going to happen at that next interval here. And you can see this will continue to go down and then back up here. So as it approaches 5 pi over 2, what is it getting closer and closer to? That would be the same as pi over 2, which is -2. And then the limit as x approaches infinity. So as this continues to go on, what is the y value getting closer and closer to? Well, it's not getting closer and closer to anything. It just keeps going back and forth between -2 and 2. So the limit of f of x as x approaches infinity would not exist. So it does not exist on E. So take a look at those, see how you did, and once again, given these graphs, can you find the limit, whether it's a one-sided limit or just the limit from both sides? So the other day we talked about using the direct substitution when we had continuous functions. But what happens when that direct substitution doesn't work? Is there other methods that we can use to find the limits algebraically? And that's what we're going to look at right now. So the first method or technique we're going to use is called the divided out technique. This is one that we're actually familiar with. Should be applied only when direct substitution produces a 0 in both the numerator and the denominator. So we always want to really start with direct substitution. So as we go to kind of answer this first question, limit as x approaches 2 of x squared minus 4 divided by x minus 2, if we use direct substitution, that would be 2 squared minus 4 over 2 minus 2. So we go ahead and try, and then what we end up getting is 0 divided by 0. So direct substitution is not going to work. But is there another method that we could use to help us answer this question? So what this means is when you get 0 divided by 0, there's actually a factor that is in common that is canceling out, that is causing that 0 divided by 0. So if we can figure out what that factor is and we can cancel it, then we can use direct substitution again to be able to figure out what that value of x approaches. If you guys remember when we did rational functions, we had points of discontinuity. And those were holes in the graph, so even though they weren't identified at that particular point, since we are now doing limits, it's once again, we don't care what happens at x equals 2, we care as it approaches it. So if you look at this limit, as x approaches 2, hopefully you recognize that it can be factored. So we are dividing it, but one way to divide is if we factor, then we can see that factor that cancels. And that's why when you plug in x equals 2, you get 0 divided by 0 right there. And so that's why, when we go to do direct substitution, it doesn't work. But now, once we factor and divide that out, now we're left with the limit as x approaches 2 to the expression x plus 2. These two functions are equivalent except at x equals 2. So we're still able to find the limit of the new function x plus 2 by using direct substitution. And then that would just be 2 plus 2, which is equal to 4. So the limit as x approaches 2 of x squared minus 4 divided by x minus 2 is equal to 4. And that goes back to that whole idea of having that point of discontinuity. Even though it's undefined, the limit still is going to exist. Okay, so let's go ahead and look at B. Here's another example. All right, the limit as x approaches 3. So the first thing we want to do is direct substitution. 3 minus 3 divided by 3 cubed minus 3 times 3 squared plus 3 minus 3. So on top you see clearly it's 0, and then on bottom you actually get 27 minus 27 plus 3 minus 3, which will also give you 0. So we have to look at using the divided out technique, which is to factor. And so obviously on top we have the x minus 3, and since we know a factor is going to cancel, we actually know one of our factors on the denominator, and the denominator has to be an x minus 3. You can also use factor by grouping on this one. So this is, if we do the factor by grouping, just so you can see the process, you take out the GCF of the first two terms, the GCF of the last two terms, and then you'll see what they have in common, the binomial. So we got the limit as x approaches 3 of your numerator x minus 3, and now your denominator would be x squared plus 1 and x minus 3. And so you can see that that factor of x minus 3, as we thought, is going to cancel out. And so now we have the limit as x approaches 3 of 1 over x squared plus 1. And since we got rid of that common factor, we can now use direct substitution again, and that's 1 over 3 squared plus 1, which is equivalent to 1/10. So the limit of this function as x approaches 3 is equal to 1/10. And then the last example here, once again, might not be a bad idea to pause the video here and go ahead and see if you can do this one on your own. Alright, so hopefully you have done that, and now let's go ahead and take a look at it. We got the limit as x approaches -2. The first thing that you want to do is direct substitution, because if it works, then there's no point of factoring or doing anything else. We would just have the answer. So we got to do direct substitution first, and then see if we need to go farther. So it looks like on top you'll get -12 plus 10, which is -2 plus 2 is 0. And so we do once again get 0 divided by 0. So we want to factor the numerator or the denominator, anything that we can, to get something to cancel. Since the denominator is already factored to x plus 2, once again we know something's going to cancel out, so therefore technically the numerator should have a factor of x plus 2. But I'm just going to go ahead and factor like I would normally. I'm going to factor out a -1. And so that just changes the signs. But then that allows me to factor a little bit easier. So that will be left with the limit as x approaches -2 of -1 times. So we got 3x times x and then -2. And once again, we know one of the factors is x plus 2, so I can use that to kind of help aid me in factoring. And double check to make sure that is correct. And then once again, you'll see the factors of x plus 1 cancel. So now we have the limit as x approaches -2 of -1 times 3x minus 1. Now we're able to go ahead and do direct substitution again. So that's -1 times 3 times -2 minus 1. So -1 times -7, which is equal to 7. So the limit as x approaches -2 of the function would be equal to 7. Now I want you to pay attention to the notation in terms of what I was doing as I was writing these. My first step is to do direct substitution, so it doesn't say the limit. It just, I'm plugging in the numbers and then getting 0 over 0. So the first part, when you're using direct substitution, you're not writing that as the limit. Once that doesn't work, then I go back. The limit as x approaches 2, I factor it out. I continue to write the limit as x approaches 2 as I simplify. And then when I'm back to direct substitution again, that's when you don't see the limit. So I'm going to pay attention to when you guys are doing this, that when you're doing the direct substitution, the limit isn't there. But when you're just simplifying things, the limit should continue to be written down until you actually go to do direct substitution again. Alright, and the other technique we're going to use is called the rationalization technique. Once again, we're only going to use this if direct substitution produces a 0 divided by 0. And we're dealing with radicals. Technically, when we normally do this, I should say, is that usually the radical is in the denominator and we're rationalizing the denominator. With limits, we don't care if it's in the numerator or the denominator. We want to rationalize it so we can create that common factor so that we can get something to cancel. So let's go ahead and take a look at this one. So once again, we'll start by doing direct substitution by plugging in 0 for x to see if this works first. And we will get the square root of 1 1 minus 1 is 0. So we do get 0 for 0 by using that direct substitution. So now we know we need to go back to the limit as x approaches 0 of the square root of x plus 1 minus 1 divided by x. So we're going to multiply. Rationalization, you multiply by the conjugate. So this, we're going to multiply by its conjugate, which is the square root of x plus 1, but instead of minus 1, remember it's plus 1. So it's opposite that. And then what you do to the numerator or denominator, you have to switch as well. Now, technically we're multiplying by 1, so we're not changing the problem, we're just changing what it is going to look like. And hopefully we're able to find that common factor so that we can get it to cancel, so that we can do direct substitution again. So on top you're just going to distribute that out. That'll leave you with x plus 1. Middle term cancels with the conjugate, so x plus 1 times minus 1, sorry. And then the denominator, don't distribute that. Okay? It'll just be x times the quantity square root of x plus 1 plus 1. So you will see on top that we get the limit as x approaches 0, so the 1's cancel, so it's x divided by x times that quantity. And that's why I didn't want you to distribute, is because now you see that the x's cancel. So we're left with the limit as x approaches 0. Still haven't answered the limit question just yet, so we need to continue to write it, of 1 divided by the square root of x plus 1 plus 1. Now that we've canceled that common factor, now we can do direct substitution. So it'll be 1 divided by the square root of 0 plus 1 plus 1, which would be 1 divided by the square root of 1, which is 1, so that would be equivalent to 1/2. So the limit as x approaches 0 of the function square root of x plus 1 minus 1 divided by x is equal to 1/2. That's using the rationalization technique. Alright, and the last thing we're going to look at is a limit from calculus, and this is really where we start to get into some of this calculus stuff. If you remember the beginning of the year, we had talked about the difference quotient, f of x plus h minus f of x divided by h, where h cannot equal 0, and we would evaluate some of those functions. We're going to be using the difference quotient right here and using a limit to find as h approaches 0. So the limit as h approaches 0 of f of 2 plus h minus f of 2 divided by h, knowing that this is the function we're going to use, f of x equals x squared plus 3. So we're going to evaluate this limit. So this will be equivalent to the limit as h approaches 0. And actually, I kind of jumped ahead right there because we need to make sure we do direct substitution first. So we'll plug in h equals 0, and let's see what happens. So this would give us f of 2 minus f of 2 divided by 0, which you can see is 0 divided by 0. So we still get the numerator and denominator to be 0. So we're going to have to evaluate this once again, looking for something to eventually cancel. So now let's go back to the limit as h approaches 0, and we're going to do f of 2 plus h. So remember, the function is x squared plus 3. So wherever there's an x, you're going to replace it with 2 plus h. So this would be 2 plus h squared plus 3. So this represents f of 2 plus h. Minus f of 2. Minus, well, f of 2 is just, if you just plug it in, it's 2 squared plus 3. And then all of that is divided by h. Alright, so what is that going to be equal to? So we got the limit as h approaches 0. 2 plus h squared, remember that is a binomial times a binomial, so that's 4 plus, that would be what, 4h plus h squared plus 3, and then 2 squared plus 3 is 7, so it would be minus 7 divided by h. So then we get the limit as h approaches 0, and then you're going to simplify that. You have h squared plus 4h, but the 4, the 3, and the negative 7, they all cancel. That's 4 plus 3 is 7, minus 7 is 0, divided by h. We don't want to do direct substitutions yet because that would still give us 0 over 0. Something has to cancel. So we still have the limit as h approaches 0, and now we want to factor out an h. So that's that divided out technique, so that you can see the h's will cancel, and we're left with the limit as h approaches 0 of h plus, let's go back there for a second. This isn't 4h if I factor out an h. It's just a 4. So h plus 4. Alright, and so now we have the limit as h approaches 0 of h plus 4. And now we can use our direct substitution, plug 0 in for h. 0 plus 4 is 4. So the limit as h approaches 0 of f of 2 plus h minus f of 2 over h is equal to 4. And so when we get into derivatives, we'll have a better idea of what all this means when we're finding the limit of the difference quotient. So that is it for 11.2, techniques for evaluating limits. Once again, looking at one-sided limits, the existence of a limit, be able to look at a graph and find the limits from the left and the right side, and then using the two techniques, the divided out technique and the rationalization technique, to evaluate limits algebraically.